It is 7th lesson and we will start a new chapter. Context-free languages. In this context, we will start with context-free grammar. This is one of the important words of the American linguist and cognitive scientist Noam Chomsky. Language is a process of free creation. Its laws and principles are fixed, but the manner in which the principles of generation are used is free and infinitely varied. Even the interpretation and use of words involves a process of free creation. According to Chomsky hierarchy defined by Noam Chomsky in 1956, depending on restrictions and complexity present in the grammar, languages find a place in the hierarchy of formal languages. In the previous chapter, we saw the regular language called Type 3. Now we will learn the context-free language title, which he calls Type -2. Within the scope of this course, we will also see Turing machines at the TYPE0 level. There is not only a Type 1 level context-sensitive topic in our lecture notes. From the point of view of natural language processing, context-free grammar aims to formulate sentences people make up. For example, if we say that a sentence consists of two parts as noun phrase NP and verb phrase VP, the different expansion states of NP and VP can be modeled as follows. After all, any sentence in natural language can be constructed or confirmed with the help of this grammar. We can think of the context-free grammar structure as follows. How can we generate a 0 to the power of n1 to the power of n word or sentence with memoryless tools just like in regular language? It may seem difficult at first glance, but there is actually a simple method. This is also a method that people with a weak memory can use, getting the job done on time. If we generate a 0 every time we generate a 1, then we don't have to worry about whether the two symbols are equal in number. It's also very easy to design as a grammar. We can create a recursion with one rule. Thus, we can expand our sentence as much as we want by adding the symbol 0 to both its left and 1 to its right at the same time. But just as every recursion operation has a stopping criterion, here too we need a termination rule. The termination rule here could be epsilon. We can use pipeline, which means OR, to write rules side by side. Formal definition. A context-free grammar is a four-tuple G equals capital V, capital Sigma, capital R, and capital S, where capital V is a finite set, whose elements are called variables. Capital Sigma is a finite set, whose elements are called terminals. For this lecture note, intersection of capital V and capital Sigma must be empty set. Don't be surprised to see that it's not mandatory in other notes. Capital S is an element of V. It is called the start variable. Capital R is a finite set, whose elements are called rules. Each rule has the form capital A goes to W, where A is element of capital V and W is element of capital V union capital Sigma star. Now, we will learn to derivate any string by using grammar rules. Here, our example is a to the power of 4b to the power of 2. First, we should label the grammar rules as 1, 2, 3 so on, then beginning from start variable, and we must expand all variables we hold. On the right are the variables we hold. In the first line, Both variables capital A and capital B are waiting to be expanded. We must find the best derivative. But we must not forget that there is no single absolute solution. In this example, we choose to expand variable A in the first row using the third rule. The derivation solution is up to you. You can show that the word is an element of this grammar by going a different way. Here, the red circles show the variables chosen to expand in the next step in derivation. For easy understanding, you can follow the derivation steps on the right parse tree. In this first example, we will model the spelling of parenthetical symbols used in mathematics. You know, when a left parenthesis is used, it has to match a right parenthesis typed later. Otherwise, there will be a typo in the use of parentheses. In this problem, we use symbol A instead of left parenthesis and symbol B for right parenthesis. There are three critical details that need to be modeled here. The first one is the nested parentheses. We need a rule to model this kind of parentheses. Capital S goes A, capital SB rule represent the nested parentheses. The second one is side-by-side parentheses. We know that the parentheses can be used in the same level. Capital S goes double, capital S rule solves this situation. The last one is termination of recursive steps. Since first two rules contain recursions, we know we must stop them with another rule. Capital S goes epsilon will make this. This is the second example in context-free grammar. Consider the language capital L equals A to the power of NB to the power of MC to the power of N plus M. So that N and M are greater than or equal to 0. As an example, the word A to the power of 3B to the power of 2C to the power of 5 is an element of the L language used in this problem. If we paint all the A symbols on the right and the same number of C symbols with blue and the remaining symbols green, we may immediately think of writing the following rules. If the rules are written without proper planning, some incorrect words may be produced. Here, we must start to write our algorithm at first. Since the definition of the language starts with the symbol A, we must first model the symbols A and C attached to it. So we think of the language as outer layer and inner layer. Once the outer layer is derived, we can move on to the inner layer. So let the variable S goes to the outer layer of first in addition. While writing each rule, it should be checked whether the language can be epsilon at that rule level, and if necessary, the epsilon rule should be added. Since the N and M values in the question can be 0, the language accepts the completely empty string. So language can go to epsilon at this level. Variable A can be derived with the symbol A from the left and the symbol C from the right. Once the derivation for outer layer A is finished, the grammar should move to inner layer B. In this rule, the grammar can be terminated with epsilon. Likewise, variable B can be derived with the symbol B from the left and the symbol C from the right. Once the derivation for inner layer B is finished, the grammar must be terminated with epsilon. That's all. Thanks for listening.